Oh, what did I do? It's getting there. Okay, here we go. Okay, there. I'll get there, I'll get there. Here it comes. Or not. Oh, there it goes. Can you guys see it? Yes?
Yes.
Okay. All right, so this is correct, though you need to write the X here. But somehow when you did your, when you did this, something went wrong. It should just end up being secant X after you simplify. So you can do it the way you did, which is like turn it into sines and cosines, but it's probably easier to just notice that on the top here, you've got secant tangent and secant squared. So you can pull a secant X out of that, and then you can, cancel the bottom there, because this will be, if I pull out a secant, I'll end up with tangent X plus secant X, and then that cancels with the bottom. So it should just be secant X in the end. I don't know exactly where you went wrong there. So for the second one, yes, this is going to be -1 over 1 minus x or u squared, and then multiply by the derivative, which is this, so that's correct. Or this third one, inverse tan is 1 over 1 plus u squared, so you have that times the derivative here. And okay, so the derivative of this is going to be the 3, okay, 1 over this times the derivative of it. So yes, that's right. Okay, good. This is multiplied, not added. So this is just multiplied by that, or this can be in the top. So however you want that, but this is all multiplied, not added together. Okay, this one is terrible. It's just not fun. Though if you do it this way, like she did, that's a good trick to make it a little bit easier to deal with. You do want a 2 then here as well, because that 2 multiplies both of these guys. So it's a little bit easier this way, or a lot of people just did it the full way, and then you have to use the quotient rule. So that's a headache. But so if you do this and break it up, that is nice, and you don't have to use the quotient rule. Then you just do 1 over this times the derivative of that, like she has here. Both of these derivatives have at least one have a product rule in them, right? So this is just ax, but then here it's the product rule chain rule. So that times the derivative, that. Here it's it's a product rule chain rule, but this is like also chain rule is just cosine 3x, extra 3 there. So then she has it all together here, and it becomes this. So that's all correct. Looks like it's all correct, except it needs a 2 here. All right. Ugh. Okay. So that's a terrible problem. So here's number 2. Take the velocity. You take the derivative for the velocity, you get this, because it's a product rule. You set it equal to 0. It's also equal to 0 at 0. But then, yeah. So, and then what she did is she made a, what do you call this thing? Sign chart with the 0 where you start and the 2, and this is the answer, right? It's positive, and then at 2 it turns around. So given that's the situation, if you want the total distance, you have to break it up at 2 and consider how far the particle goes from 0 to 2, and then how far the particle goes from 2 to 6, absolute values here. And then that's what you get. Okay, is everyone all right with that business with the total distance and how you have to break it up and why? Because I know that can be confusing. Okay, so this is something. Okay, good. All right, now when it comes, okay, here you have made us an error because when so you're going to take the derivative again of this, and so when you take the derivative, I don't know how you got 3. So take the derivative of this, and it's a little bit more complicated than that. If you end up with a quadratic. Okay, here's your derivatives. Okay, so what happened here? This is right. 2t. Okay, so this is supposed to have a 2 here. And that might just be it. Yeah, I think that's it. So this has a 2. This should be, that has a 2. And then these 2 t's, and this is 2t, and they actually both come with a negative, so that should be 4t. We got that. Okay, yeah, so that's right. This is supposed to be a t here. And then this is supposed to have a 2. So what you should have, so you just made a couple of small errors. -2. Yeah, -2. I think it's that. This guy, let me track back. This guy's supposed to be plus. This one times it, yeah, supposed to be plus. Okay. All right, so this is actually what the acceleration is. So then you have t squared minus 4t plus 2 e to the minus t. And then where this is equal to 0, here, let me do this. By the way, guys, let me do here. So where this is equal to 0, this guy's never equal to 0, so you just have this. I'm not fully convinced that this is a plus 2. Let's see. I have to go back and start from the beginning then. But so it would be minus b plus minus the square root of b squared. Yes, it is. That's right. That's the right answer. All right. Because this is square root of 8, so it's 2 root 2. So I end up with 2 plus or minus the square root of 2. That's what, yeah. So that is right. So those are your 2 points. And then if you think about both of them are greater than 0, right? So if I look at my acceleration, I've got 2 minus the square root of 2 and 2 plus the square root of 2. And so if I look at something here, this can be minus plus plus. And then you can, solve, okay, so here it's slowing down and there it's speeding up, right? Okay. Yeah, so I would go back and re-look at those. It shouldn't look like that. I don't know. I will go back and regraph those, especially so with the everything, the with fix up that one. Okay. So any more questions on that one? No? It's okay? All right, so let's go on to, Tristan says she had other ones. Yeah, you see how she did it slightly differently? She didn't break it up, so it makes it a little bit worse in that sense because you have to use the quotient rule. But you know, this is the crappy situation. So what are you gonna do? Okay, so okay, here we go. So for all of these A, B, and C for this population growth one, you basically do it the same way. You start off with this, you know that it's going to be something like this, why not e to the KT? And then you use the information that they gave you. Oh, okay, here it is. So the information that they gave you, so they said for A, you start with the data from 1950 and 1960, right? So what she did here was she didn't write it down entirely, but she let T equal 0 at 1950. That means that the original population is the population at 1950, which is 83. And then she knows that the population at 1960 would be 100, but if T equals 0 is 1950, then T equals 10 is 1960. So that's why it's 10 here, 100 equals 83 e to the 10K, and then she used that to solve for K. And when she's got K, she puts that back into here and can figure out what the population should be at 30, which is 1980. And you see it came a little bit too low, right? It came at 145 when the actual population was 150. So then she did the same thing for the other two. So they want you to redo the calculation with different data to change, and the K changes a little bit every time. So for part B, you get 225, and the population is supposed to be 214, I guess. And for C, she got 255. So she got two that are too high and one that was too low. And for D, she figures it's going to be too high. And because that's what the last two were a little bit too high. Fair enough, right? And so the question here is well, just think about it. And of course, right now we're in a pandemic, so it's sort of obvious that there's like a lot of reasons that population growth can change, right? And so just thinking about that's going to give you what you want for 3E. So yeah, sounds good. Okay, so for the last one, this is a very straightforward related rates problem. Okay, somehow the number went off here though. So I see what happened. Okay, so starting off with this. Okay, yeah, so X is here. She's gonna make X the hypotenuse and Y and Z the leg. So she did that, that's right. So what we want then is to solve for dz dt, which is how far the boat is moving over here. So if I look at this, if I look at this and I see what you did, you put in the 9, but actually what you want to do is not put in the 9 there. Because if I take the time derivative of this thing, y is not moving, so its time derivative is 0. So it effectively, it should just be 2x dx dt equals 2z dz dt. So let me, it's almost like if you put in a 3 first and then take the derivative, that works too. So you have x squared equals y squared plus z squared. Let me stop share here. So you have this, and now y is the dock. So that's 3 meters, and it's not changing. So if I put in, I get x squared equals 9 plus z squared, and then when I take the time derivative here of everything, I'll get 2x dx dt equals 0 plus 2z dz dt. Okay, and then you can solve from there. The other thing you can do is you can take the time derivative of everything there like this, and then because the dock isn't changing in size, this is just 0 because dy dt is 0. So some people prefer to do it that way. I tend to prefer to do it this way, where if one of the parameters is constant throughout the problem, I'm going to put in that constant number because then I don't have to think about this. But some students prefer to do it this way. That's fine. But when you take the derivative, either way, that 9 knocks out. So that's why her answer is a little bit off because she had a 9. So in the summit, in the end, we're looking for dz dt. It was like this, z and x. And so they gave you x equals 5, and she did that. She figured out that when x equals 5, z equals 4, so it's 3, 4, 5 right triangle. So then plugging in all this stuff, x was 5, z was 4, dx dt was 2, right? So you end up with 5/2, what was it, meters per second? Yeah, that's what you want to have. Okay. One more thing I had to say about this. It's okay here because everything is moving in the same direction. So it works out one way or the other. And they asked you for speed anyway. They didn't ask you for any kind of direction or velocity or anything like that. But for some of the problems, it matters whether the parameter is getting bigger or getting smaller, right? Here, as we pull in our rope, both the distance on the rope is getting smaller and the distance from the boat to the dock is getting smaller. So both of these are getting smaller. So technically this should be a minus here, and then that would percolate to being a minus here. But it really, since they didn't ask you about the direction, it doesn't make a difference in the problem. I wouldn't take off points there or anything. But you will notice in some of the ones we do next week, it starts to matter whether the quantity is increasing or decreasing, whether the rate is positive or negative. Okay. So does anyone have any other questions? No? We all good for this week? Not nothing. No, when is Wayne State Mental Health Day? I got an email about that, but I didn't read it because I had so many emails. What what day is it? Next Friday. Oh, but that's bad. We have a test that day. That's not a good mental health thing. When did it become mental health day? Well, they couldn't, like, if they had told us that in the beginning, I would have switched it around. Oh my gosh. Well, I don't know exactly what to do about that one, but it's going to be, oh, you guys also, we can also change because there's a, I guess we had our tests in this class that evening too. If you guys want though, we can do it on a different day. But I don't know if I can get one in Thursday. That's becomes a problem. It would have to be Saturday. All right, I'll give some thought to that, okay? Yeah, I know you don't want to take a test on Saturday. But I will give some thought to that and see if there's something else we can do. Yeah, that is Halloween. That would be terrible. That's even worse. All right. Okay. Right. Thanks, everybody. And we'll see you next week then. All right. Bye-bye.